The end behavior of a graph is the behavior of a graph as x approaches positive or negative infinity. There are 4 types of polynomial functions. The first one shown here is an odd degree and a positive leading coefficient. In this graph, as y approaches positive infinity, x approaches positive infinity for the part of the line going up, and as y approaches negative infinity, x approaches negative infinity for the part of the line going down. The second one shown here is an odd degree and a negative leading coefficient. In this graph, as y approaches positive infinity, x approaches negative infinity for the part of the line going up, and as y approaches negative infinity, x approaches positive infinity for the part of the line going down. The third one shown here as an even degree and a positive leading coefficient. In the graph, as y approaches positive infinity, x approaches negative infinity for the part of the line on the left side, and as y approaches positive infinity, x approaches positive infinity for the part of the line on the right side. The fourth one shown here is an even degree and a negative leading coefficient. In this graph, as y approaches negative infinity, x approaches negative infinity for the part of the line on the left side, and as y approaches negative infinity, x approaches positive infinity for the part of the line on the right side. There are some special product patterns that may be reviewed but are important to memorize and learn. A plus b times a minus b equals a squared minus b squared. A plus b squared equals a squared plus 2ab plus b squared. A minus b squared equals a squared minus 2ab plus b squared. A plus b cubed equals a cubed plus 3a squared b plus 3ab squared minus b cubed. A minus b cubed equals a cubed minus 3a squared b plus 3ab squared minus b cubed. This is Pascal's triangle. You can use Pascal's triangle to expand binomials. For each row of Pascal's triangle, which we will call the nth row, the numbers on that line of Pascal's triangle give the coefficients of each term, a plus b to the nth power. For example, the fourth row represents the coefficients of the term in a plus b to the fourth power, and the expansion is 1 times a to the fourth power plus 4 times a cubed plus 6 times a squared b squared plus 4ab cubed plus 1b to the fourth power. When doing polynomial long division, write the polynomials in long division format and write 0 as the coefficient for x squared, which is your dividend. For each step, divide the term with the highest power with the first term of the divisor. This example shows an example of a polynomial long division problem. There are many ways to factor polynomials. One method is to find the common monomial factor. To do this, factor a common monomial and then factor the polynomial. Another method is to factor the sum or differences of the two squares or cubes. First, you write the polynomial in the form a cubed minus b cubed. Then, using a special factoring pattern, factor the sum or difference of the two cubes or squares. Another method is to factor by grouping. Write the polynomial in order of the term with the largest degree to the smallest degree. Then you factor the polynomial in groups of 2 and combine them. First, you have to set the polynomial equal to 0. Then, you factor it using any method of factoring such as grouping or the quadratic formula. The solution is also the solution to the polynomial equation and the roots of the polynomial, while also being the 0 of the polynomial function. You first want to check if the polynomial has integer coefficients. An integer coefficient includes every rational solution of f times x equals to 0. Afterwards, you want to know that p equals any factor of the constant term, that q equals the factor of the leading coefficient. This is useful for finding all real solutions of polynomials. The fundamental theorem of algebra states that polynomials with a degree greater than 0 has at least one solution in the set of complex numbers when f times x equals 0. The corollary to the fundamental theorem of algebra states that polynomials have n solutions when the polynomial has degree n as long as n is greater than 0. The complex conjugates theorem tells us that polynomials with coefficients that are real numbers and that have a plus b times I as an imaginary 0 or solution have a minus b times I as another 0 or solution of the polynomial. Descartes' rule of signs states that if a polynomial has real coefficients and are ordered from the term with the largest degree to the smallest degree, then the number of positive zeros or solutions is equal to the number of sign changes, either plus or minus, of the coefficients of f times x, or they can be less than the number of sign changes, which can be calculated by subtracting 2 until you reach 0. For example, if a polynomial has 5 sign changes, it can also have 3 or 1 sign change. Descartes' rule of signs also means that the number of negative zeros or solutions is equal to the number of sign changes of the coefficients of f times negative x, or it can also be less than the number of sign changes, which is calculated by subtracting 2 until you reach 0, similar to the previous procedure. For horizontal translations, which are shifts that go left or right, f times x turns into f times parentheses x minus h. If the h is positive, the graph shifts right. If the h is negative, the graph shifts left. For vertical translations which shift up or down, f times x transforms into f times x plus k. If k is positive, then the graph shifts up. However, if k is negative, the graph shifts down. For reflections which flip over the x or y axis, it depends on which axis something is reflected over. For reflections over the y-axis, f times x turns into f times negative x. For the x-axis, f times x stays the same, f times x. For a horizontal stretch or shrink, stretches or shrinks from the y-axis, f times x turns into f times parentheses a times x, and if a is greater than 0, then the graph shrinks by a factor of its reciprocal. If 0 is less than a, which is less than 1, the graph stretches by a factor of the reciprocal. For a vertical stretch or shrink, stretches or shrinks from the x-axis, f times x turns into a times f times x, and if a is greater than 0, then the graph stretches by a factor of a. Then, if 0 is less than a, which is less than 1, the graph shrinks by a factor of a. Zero-factor solutions and x-intercepts are equivalent, or are the same thing. The local maximum and the turning point of the graph of a polynomial function when the point is higher than its nearby points, while the local minimum is the turning point of the graph of a polynomial function when the point is lower than that of its nearby points. This graph shows the local minimum. This graph shows the local minimum when f times negative x equals f times x for all values of x. The function is an even function, which when graphed is symmetric about the y-axis, while when f times negative x equals negative f times x for all values of x, the function is an odd function, which when graphed is symmetric about the origin. While using 3 x-intercepts, write the function in factored form. For example, if the x-intercepts of a graph were negative 2, 0, and 4, and 0, the function in factored form would be a times a parentheses x minus 2 times parentheses x plus 4. Then substitute any points beside x-intercepts into the function and find a. Finally, substitute your solution for a. Thank you for watching, and we hope you enjoyed this tutorial.